Hey, welcome to the greenhouse. I'm Alex. Today we're going to talk about trees. So I've got 3 questions about this tree. What does it weigh? How do you even weigh a tree? And where does that mass come from? Let's answer question number 3 first.
Trees are made out of thin air, meaning their mass comes from molecules in the atmosphere, carbon dioxide gas, and rainfall. Photosynthesis builds the biomass of plants, allowing tiny acorns to grow into enormous oak trees. In a leaf, chloroplasts near the upper surface capture energy from the sun. The lower leaf surface contains pores called stoma that allow gases to flow in and out, and veins bring water from the roots to the leaves. Sunlight drives the chemical reaction between water and carbon dioxide that produces carbohydrates like glucose. The remaining oxygen exits the leaf through the stoma, and the carbohydrates move through the vein system, building the biomass of the tree. So in a tree, approximately 50% of its biomass is derived from the carbon that enters the leaves as the invisible atmospheric gas, carbon dioxide. Okay, so the mass of the tree comes from carbon dioxide. Back to our other 2 questions. Can we measure the mass of a tree and find out what it weighs and how much CO2 it holds? One way to do that would be to cut it down and cut it into small enough pieces to put on a scale, but that job itself is difficult and it's certainly hard on the tree. If we could measure or estimate the volume of a tree, we could calculate its mass. But trees have very irregular shapes, and it might at first seem difficult or impossible to calculate the biomass of such an unusually shaped object. Here, the field of allometry can help us. Allometry is the numerical relationship between one part of a living thing and the whole organism. So foresters have already cut up, and weighed lots of trees of different species and have worked out the relationship between the measurements of height, diameter, and the biomass of the tree. Here's a graph of the relationship between a tree's diameter and its mass. As you might expect, the relationships are a little bit different depending on the species of tree. And we can't measure diameter directly, so we measure the circumference and use the relationship between the perimeter of a circle and its diameter to calculate the diameter.
All right. This is a tree cookie, and we're going to take a look at the relationship between the diameter and the circumference of this. Okay, so what's the relationship between the circumference of the tree and its diameter? If this were a real tree, we wouldn't just be able to take our tape measure and measure across the diameter because, of course, the tree's growing. So we have to measure the circumference. So let's do that. Okay, so here's the circumference is 2 meters and 15 centimeters, and that's going to be related to the diameter of the tree by a factor of pi. So we're going to measure the diameter of this tree. We do diameter at breast height, roughly about here. I'm going to use the centimeter side of my tape measure, wrap it all the way around the tree, and see that we have got 122.5 centimeters. That's the circumference of the tree.
Once we've got the diameter for our tree species, we can read the biomass off the graph. So this honey locust with a diameter of 39 centimeters has an above-ground biomass of 1,000 kilograms. That's 1 metric ton. Notice that the chart we used here tells us the above-ground biomass of a tree, but of course the tree grows roots as well as branches, and we'll need to factor those in. A typical tree has about 80% of its mass above ground, while the roots make up the remaining 20%. So we can adjust our calculation to find the total mass of the tree. Once we have the biomass, we can take this one step farther, and we can figure out how much carbon dioxide this tree has taken out of the atmosphere. All we have to do is add in a few more facts about the tree and about carbon dioxide. So here are 2 rules of thumb about trees. The mass of a tree is 50% carbon, the below ground roots are about 20% of the tree, and the above ground trunk and branches about 80%. Let's measure a bigger tree and work through the whole calculation to see how much carbon dioxide it's stored.
Okay, for a really big tree like this one, we need our big tape measure and we need a friend. So I'm going to hold it right here at the beginning, hand it to you, send that all the way around the tree. And we've got 3 meters and 11 centimeters. Wow.
Okay, so we'll use this table to help us go through the calculation step by step. First, enter the circumference that we measured, 311 centimeters. Then divide by pi to find the diameter, 99 centimeters. Next, we go to the biomass chart and find the corresponding above ground biomass for a maple tree with a 99 centimeter diameter, and we see that it's 9,600 kilograms. Okay, now we have to account for the mass of the roots, which we can do by multiplying our above ground biomass by 1.25. This gives us the total biomass. So now we've answered 2 of our original questions. What does a tree weigh, and how do you weigh a tree? But we also want to know the mass of carbon, or carbon dioxide, that was taken out of the atmosphere by the tree and turned into stored biomass. Remember, we said that half of the mass of the tree is carbon, so finding the mass of carbon just means dividing by 2. And finally, if we want to express this as the mass of carbon dioxide, the mass of carbon is 12 and oxygen is 16, so 2 oxygens plus a carbon is 44. The mass ratio of carbon dioxide to carbon is 44 to 12. Therefore, to find the amount of CO2 stored in the tree, we multiply the mass of carbon by 44 twelfths. So, this tree removed and stores 22 metric tons of carbon dioxide from the atmosphere.
So, 22 tons of carbon dioxide. Good job, tree.